Hello everyone, my name is Kathan and today we'll be discussing the problem creating strings from the introductory problems of the CSES problem set. Let's begin. Let me read out the question for you. So we are given a string and our task is to generate all the different strings, that is all the unique strings that can be created using its characters, that is all the possible unique reorderings, unique arrangements or unique permutations, right? So maybe it's a good time to revisit those permutation combination formulas once a while, right? Or the concepts in general. So input. The only input line has a string of length n. We'll be given a string and each character is between a to z, right? So we are only dealing with 26 unique characters here. Output, first print an integer k, the number of strings, number of unique strings that we have or number of unique permutations we have. Then print k lines, the strings in alphabetical order. The constraints here are pretty low and this also rings something in your head. So I'll come to this very low constraints and how you should tackle such questions. So that's the beauty. Because of these low constraints, this question becomes very simple. So I'll come to this, don't worry. For example, the input they have given here AABAC. So this is a 6 length string. Now, of course, like these are the 20 possible unique reorderings or 20 possible unique permutations possible. But if you want to quickly fact check, if you know a formula for this, like number of unique permutations when some characters are repeated, the formula becomes like n factorial divided by a factorial into b factorial, where a is the, you can say, the repeat frequency of the first character, b is the repeat frequency of the second character, so on. So here, like these are 5 characters if I'm not wrong. So the total permutations could have been 5 factorial, but since a is repeating 3 times, we will have to avoid the overcounting of 3 factorial, so we just divide by 3 factorial. So 5 factorial divided by 3 factorial. So in a way, it's simply 5 into 4, then 3 factorial gets cut. So that's why 20. So like this formula can be verified. If you forgot on this formula, I'll probably link a blog on like this is, I guess, called permutation with repetitions. This was the concept. So I'll link it in the description box. You can revisit this concept of permutation combination. But yeah, I mean that's the question. You'll be given a string. You just print all the unique permutation of this string. So that's the question. Let's go to the iPad and understand this question even bit more. A lot of time what happens in competitive programming is you will scratch your head to find an optimal solution for a problem, but you won't be able to find it. Only to find out that you are not expected to code that optimal solution. Why do I say this is, look at the constraint here. N can be only as high as 8. So even if you find the worst possible solution here, which can be, you can say, n power n, which is 8 power 8, this number also turns out to be somewhere order of 1e7. So like even if you have the order of n power n solution, it will run in 1 second and it will be accepted, right? So such low constraints automatically tells go for brute force, right? Happily go for brute force, right? That's what they are expected, right? So it's a hard problem. There is a probably no optimal solution for it, right? So that's why brute force is allowed. Let's come back to a problem. So we are given a string, right? So let's say we have a string of length 3. I'll take a small example here and try to show you what they are expecting. Let's say we have only 3 unique characters right now, A, B and C. So this was the string given to us. Of course it will be ABC, but I am representing a string as character arrays. So how many possible permutations are there? So that's what they're asking, right? All the possible unique permutations in sorted order. The sorted order is a very easy task to deal with. You can just store all of them in a set and print them. So that's not a big deal here. But what are these 6 permutations? How do you create them is what we are after. So let's see. So for n equals to 3, you know all the possible unique permutations are simply 3 factorial, which turns out to be 6. What are those 6? First is ABC, then we have ACB, then we have BAC, then we have BCA, then we have CAB, then we have CBA. These are 6 possible permutations. Let's take one of them with a duplicate because like that's the most interesting part of this question. Let's say we have characters AAP. So here, of course, all the possible ways to reorder 3 characters or 3 elements is 3 factorial. But since this A is repeated 2 times, you will have to divide it by 2 factorial, right? So I guess this is a classical formula of permutation with repetition. It turns out to be n factorial divided by a factorial into b factorial into b factorial into c factorial, where a, b, c are, you can say, the frequencies of the repeated element, right? So this is, you can say, a quick refresher of your P and C classes in your plus 2. Fine. So Here 3 factorial by 2 factorial, which is 6 by 2, which turns out to be simply 3. So there are only 3 possible unique permutations possible. And what are those? They are simply AAB, ABA, and BAA, which again apparently I guess I have written all of them in a sorted order. So this is what is expected. You have to print them, and you also have to print two things. You have to first print the count, and then you have to print these guys, right, in sorted order. Fine. So let's see, like, how can you form a permutation. Of course these all are very easy to remember, but you cannot generate them without any pattern. So there has to be some pattern to generate this permutation, right? So let's try to figure that pattern out here. For now, let's just deal with unique characters, right? The duplicate part I'll come to bit. Otherwise, it will make things a bit complicated. Initially, let's assume we have only unique characters, right? So let's see what can be done. Let's say we have characters A, B, C, and we want to find out all the unique permutations which are possible. Now you know these are 6, but can we come up with a pattern to generate this permutation? Turns out we can. So let's index them 0, 1, 2. Now what can happen is a permutation, or you can say reordering, can either start with A, right? So it can either start with A, or it can either start with B, or it can either start with C, right? Once it starts with A, you have only 2 characters left at your disposal, B and C. Once it starts with B, you have only 2 characters left at your disposal, A and C. Once it starts with C, you have only 2 characters left at your disposal, A and B, right? So now for the second character, you again have some choices here, right? So for the first character you had 3 choices, A, B or C, right? So there are 3 choices here. Fine. Similarly, for the second character, if you come through this branch, that is, if you have chosen A as a first character, you have 2 options. Either you can choose B or you can choose C, right? So if you choose B here, then you only have C left as your third character. If you choose C here, you only have only B as your third character choice. Similarly, if you come here, then you decide to choose B as your first character, then as a second character, you have again 2 options. Either choose A, then the third character will be left with C, or you choose C. Third character choice will be simply A. Similarly here, if you choose A or B, so if you choose A, you'll be left with B, and if you choose B, you'll be left with A. It turns out in this way, what you have done is now only one character is remaining. So effectively, you have created a permutation ABC, ABB, sorry, ABC, so here you can finally see your permutations coming into place. So for example, A, B, C is the one permutation, A, B, and in this tree you can see all of the 6 possible permutations. For example, one of them is ABC, then ACB, then BAC, then BCA, then CAB, and CBA, right? So it gives a hint, like to form the permutation, you can employ a sort of a recursive strategy. And how do you apply that? Let's just see. Okay, so what do we have here is we have 3 characters to choose from, A, B, C. Let's index them 0, 1, 2. What you can do is this time I'm trying to come up with a recursive strategy here and create permutations. So let's just take an empty bucket here, or maybe let's just call it an auxiliary array, or you can say in this bucket I'm gonna create the permutations, and whenever a permutation is ready, I'm gonna store them in my final answer, or maybe print it, whatever I want to do. But in this bucket is where I'll store my current permutation, right? So let's just say we have a bucket here, or you can say auxiliary array, and fine, let's just see. So what do we have is, for the first character choice, we have 3 options. Either we can choose A, B or C. Let's say I decide to pick the guy at the 0th index. If I decide to pick a guy at the 0th index, what I am left with is, firstly, in my bucket I have put A, right? So in my permutation now starts with A, and now I'm left with B and C, right? Or I can choose, or I can choose, or I can choose to pick the first guy, the guy at the first index. So my bucket starts with B. So in the way, my permutation starts with B now. Fine. So I'm left with simply A and C to choose from. Okay, cool. And or maybe I could have choose the guy at the second index. So now I am left with simply A and B, and my bucket has C. So my permutation starts with C. Right? Fine. So when you are here, so when you are at this level, you've effectively chosen the first character of your permutation. Fine. Let's go next. So here you can say still you have index 1 and 2 to be considered, you have index 0 and 2 to be considered, you have index 0 and 1 to be considered. Now here you have two options, either index 1 or 2. Let's just choose, we have two options, right? Either index 1 or 2. If you choose index 1, your bucket will look like AB, but now you'll be left with only one option, C. If you choose 2, then your bucket will look like AC, but now you'll have only one option, which is simply B. Right? So you can say here second character is remaining, here first character is remaining. Fine. Okay. So here again you have two options. You can pick either 0th guy or second guy. If you pick the 0th guy, your bucket will look like BA. Right? And you will have only now one option, which will be C. Which will be C. Right? Similarly, either if you pick the second guy, then your bucket will look like BC. And you will only have one option now, A here remaining. Similarly, here you can do the same. So if you choose the 0th guy, your bucket will look like CA, and you will left with just B. If you pick the first guy, your bucket will look like CP, and you will be left with A. And now at the end, you will have no option. Your bucket, you have only one option to consider, so you will have ABC here. Here you will have in this part also you have no option but to consider the first guy, so you will have ACB. Here you have no option, so you will have BAC. Here again you have no option but to consider A, so you have BCA. Similarly, you will have CAP here, then you will have CBA here. And now that the auxiliary array size here at the bottommost level has become equal to the size of the string, which is n, you can stop the recursion here. And these, ladies and gentlemen, are your 6 possible unique permutation of string S. Right? So we had ABC, and you can verify for yourself ABC, ACB, BAC, BCA, CAB, CBA. These are all the possible unique permutation that I already listed here. Right? So how do you implement this then? Like, this is a recursive approach. So what happens is initially at the first character level, you had n possible choices. Then at this level, after choosing the first character, you have n minus 1 choices. Then you have n minus 2 choices. So on, these choices start from n, then you have n minus 1, n minus 2. So this actually makes sense also, right? So n minus 1, n minus 2. So isn't it how n factorial is made? So that's why this recursion tree makes sense. But enough about the recursion tree. How are you going to implement it? That's the real question. So once you have this recursion tree, it's actually very easy to convert it to a recursive pseudocode and then the implementation, of course. So what do you need here? Just see. Of course, like this is the top level recursion call, right? So here you'll need the string, of course. You'll need this auxiliary array, or you can say it's a data structure. So what it does is it effectively stores the current state of permutation. For example, what does this state of this data structure auxiliary array say? This CA says first, like the AC says, you have first chosen 0th guy and then you choose the second guy, hence AC. Right? So here I've written it like a stack, but it's actually horizontal, right? Just to save space, I've written it vertically. But this BC means first you have chosen B and then you have chosen C. That's what this auxiliary data structure means. Fine. What else do we need? Notice one thing, at every level, whenever you make a choice, you also need not consider a already selected element, right? For example, let's say you are here. So when you are here, you are not choosing the 0th guy again, right? So when you are here, you know for the fact that the 0th guy has been considered. So don't consider it again. For example, when you are, let's say here. So here, you know for the fact that this first index guy and the second index guy has been considered. So don't consider them again. You have only one option. So we need a way to find out what elements are considered and what elements are not. So for that, what you can do is you can maintain a sort of a flag array. Let's say it has also index 0, 1, 2, and it keeps track of which character is already part of a permutation. Specifically, if a character at this index is already present in your data structure right now, that is, you have already considered as a part of your permutation. So if it is already part of your permutation, current permutation right now, you cannot consider it again, right? So initially, you can initialize all of them to 0. And how does this state change this? Let's say you come here, you decide to pick the 0th guy. So at this point, the flag array, we are gonna mark the 0th guy as 1, right? Because you have chosen the 0th guy. So at this point, don't choose the 0th guy again. Okay, so fine. Similarly, let's say you come here, you already chosen the 0th guy, and now you're choosing the first guy. So at this point, we already have 0 marked as 1. Now you also mark the first guy as 1. This is already 0, 0, 1, 2. Fine. Similarly, if you are here, the 0th guy is already chosen, so it is marked as 1, but you also mark now the second guy. Similarly, right? So this is how the state changes. For example, if you are here, you are choosing the guy at the first index, rest through are zeros. Fine. So you will need this something. Let's just call this as a flag array, right? Let's call this as a flag. Okay, maybe it got cut. So this is called flag array, right? So these three things are very important, right? So this auxiliary data structure to store the permutations, right? So whenever the auxiliary data structure size has become equal to n, you have got a permutation. This flag array to actually know which character to consider and which character to not consider. So now that we have all this figured out, let's try to write the pseudocode, right? Because pseudocode will help us implement the solution. So here f takes, of course, s, then it takes the auxiliary array, and it also takes the flag array, right? So if you are confused, this is aux and this is my flag array, right? So if you can just relate, if you want to relate to the recursion tree that I've just drawn. Fine, cool. So what do? We go from 0th guy till the last guy, which is n minus 1. So n is simply length of s, 0 to n minus 1. Then what do? We first check if flag of I equals to 1. So this guy is already in the auxiliary array, right? So for example, if a is already in the auxiliary array, you are not going to consider it again. So we just continue. We don't consider this guy. Just continue. Don't consider this guy as part of permutation. But if it is not, what you can do is you can add this guy in your auxiliary array. So you can just maybe auxiliary.pushback or something, whatever your programming language provides. You can add it or insert it. Just the order should be maintained. So auxiliary.push, you can just add s of I, right? It's like adding a into the auxiliary array. Fine. And what else do we have to do? We have to, of course, mark that this element has been chosen. Flag of I is 1. Now the problem recurses, right? So we are gonna call f again with string, same string, but the state of auxiliary array has been updated and the state of flag has been updated, right? For example, when you choose the first guy, when you choose the 0th guy, you update the auxiliary state and the flag array, and the same call repeats. So f s aux, this is fine. And then once you have considered all the possible strings for this part, you will have to backtrack. In the sense, once you have generated all the possible strings starting with the 0th guy, you have to reset the state. In the sense, once you're done here, when you are going back from here, you will have to reset, right? You have to make this guy 0 again and remove this a here. Why? Because then you will be able to add 1 here and add b here. Again, I guess this requires a little bit more attention. Let's say I find out all the strings starting with b. I have traversed this path, right? I find out these two permutations. When I am here, so when I'm going back and I'm about to start all the possible permutations starting with c, what I have to do? I have to remove this b and I also have to reset this. Why? Because this step is gonna add c here and gonna set 0, 0, 1. right? So that's why this step is usually very confusing for beginners, but you will have to do aux dot pop back, pop or whatever your library provides. Just remove the last guy that you added, and also flag of I will be 0, right? This element is in no longer use, right? You have already considered all the elements starting with A. Now we are going back, you don't consider it again. That's why. Fine. So that's that. All that remains is base condition. When are you gonna stop the recursion? So the base condition is as simple as it can get. If length of my auxiliary array has become n, you got a permutation, right? So you have got a permutation. So whatever you like, this aux has a permutation, right? So that's that. What you can do is maybe you can store this auxiliary array somewhere, like this auxiliary string somewhere, and that will be like, you can collect all the auxiliary strings into vector of string or whatever to do, or you can maybe just print it. So that's the pseudocode of this recursive approach. You just consider all the possible characters at a given level that are available to you, and at the base level you will have all the permutation generated. I request you to like maybe go through, like draw this recursion tree yourself once, then you'll understand what happened here, because I guess this idea is reused a lot of times in recursive based problems. You'll see it occurring one more time in this playlist. Fine. So let's talk about the time and space complexity here a bit, and how can we adapt it to our solution, right? Because if you have not forgotten, this solution is still only gonna work if we have unique characters, right? Because if these characters are not unique, you will of course see some repetitive permutations forming here. So what are you gonna do? There are 2 points. First is repetitive permutation. So this is very easy to tackle, this repetitive permutation task. Why this is very easy to tackle is, what you can do is, whenever a permutation is generated in this base case, you can just store it in a set of string, right? In a set of string. So it has 2 benefits. Storing, whenever a base condition occurs, just store the result into a set of string, maybe just call it results, right? So whenever permutation occurs, you store in this result. 2 benefits: the results will be sorted, which is what is expected from you, and no duplicates will be there, right? So just storing the results in a set at base condition solves your issue. So repetitive permutation and sorted order, both are done if you just store the auxiliary results in a set. And let's discuss the time complexity, like लगे हाथ वही भी वो भी कर ही लेते हैं. So the time complexity discussion might look scary, but it is actually not. Now in this questions, when the time complexity is going exponential, there is a very neat trick you can exploit from the trees. So there is a very interesting property of trees, like it's going exponentially, right? So there are 3 branches, then there are two branches for each of one of them, and so on and so forth. Now the leaves that you have got, there itself so many, these leaf nodes means the nodes at the last level, are so much that they dominate the number of, you can say total number of nodes above it, right? Because the exponential, right? So the branches have grown so much, the number of leaves are so many compared to everything above it. So what you can do is you can just find out how many time is spent at the leaves, and that will be a good approximation, because the number above it will be just some constant time more than that. So asymptotically, it doesn't change anything. So what you can do is, the total time complexity turns out to be n factorial, because we'll have n factorial permutations at the bottommost part, leaves, right? And for each one of them, what do? We use, you can say, we try to insert it into a set, right? And every permutation can be of size n. So there can be order of n time, because for every n character to get inserted, and since it is a set, it will consume log of something, log of n factorial something, depending on whatever the size of set is. So there will be some logarithmic factor here involved. All in all, what I'm trying to say here is, the total time complexity still is very less, because n cannot go beyond 8, right? N cannot go beyond 8. So this thing is still very less, right? So that's what I'm trying to say. So this is a time complexity, order of n factorial into n into log, right? So this because we have n factorial permutation, this because we are inserting into set and all, right? So That's why. And what about the space complexity then? The space complexity here is simply order of n factorial, right? Because we are storing all the permutation into this set. So that's why the space complexity is order of n factorial. Space complexity is order of n factorial because we are storing all the n factorial permutations. But there's one more space which has to be talked about. This is all recursion, right? So this is not going to happen anyway. To store this recursion calls, we'll need some stack space. So what are the number of levels here? We have n characters to choose from. We have n minus n characters to choose from. We have n minus 2 characters to choose from, so on and so forth. So we start with n, go to n minus 1, so on till 1, right? So, and at a time, if you observe, only one of these function calls will be happening for obvious reasons, right? So if you are here, you have nothing to do with these functions. So our recursion stack space effectively will be the depth of this recursive tree. So it turns out to be order of n. So n factorial for storing the permutation and order of n for the recursion stack space, right? So that's about the space complexity. Now let's continue with the optimized approach where we try to get rid of. Now it turns out there is an optimized approach to this where you can get rid of this space and make it order of 1. So you can not store the permutation, you can just print them. That you can actually do. And this you can get away by not using a set. So the time complexity then will be simply order of n factorial into n. Why n? Because you still have to print them, right? So that's why order of n into n factorial will be the final time complexity that you can get. So how do you approach that then? Let's see. I'll show you how that can be approached as well. So this time, let's take a string with duplicate characters. Let's say we have AAP. So n is 3 here, right? Now the approach is, this is also of course a recursion based approach only. What you do is you convert this into a frequency map. So here A has 2 characters and B has 1 character. Now a frequency map, just store them in sorted order, okay? Storing them in sorted order helps because then you will create the permutation in sorted order, right? So sort this map, so maybe just use the map that is provided to you, or you can just create a, you can say a vector as well of size 26 because we only have A to Z characters, right? So first things first, you just create a frequency map. You do whatever you want, keep it simple, just create a normal map, but make sure that these characters are sorted. Fine. So once you've created it, what you do is our approach is a bit different. See, we will still have our auxiliary array, or you can say the data structure where we will dump our permutation, what we have currently. What is our approach this time? Instead of indexes, just consider what all unique keys are available to us. We have 2 unique keys available to us, right, at the first level. So now this is where the topmost recursive call will happen, right? You give the frequency map in the auxiliary array where I'm going to store the current permutation state. So instead of what possible indexes are available to me right now, I'm going to ask myself what possible unique keys are available to me. Here I want, of course, 2 possible unique keys available to me. So let's say I choose A, right? So if I choose A, in my auxiliary data structure, I'm going to add A and I'm going to update the frequency map. I only have 1A available now. I only have 1B available now, right? So here I chose A, fine, but I could have chosen B as well, right? Because I have 2 unique keys available. So if I choose B, then my frequency map now only has 1 unique character, A available, but my auxiliary data structure has B, fine. Okay, let's see here. So this is simple, right? So you have only 2 unique characters available to your disposal, either you choose A or B, fine. So let's come here. Ask yourself a question. What unique characters are available for me to choose? Only 2. Either I can choose A or I can choose B. Fine. So if I choose A here, my auxiliary data structure will look like AA. But now I'll only have 1 option to choose from, B. If I choose B, then my auxiliary data structure will look like AP. But now I'll only have 1 option to choose from, which is A1. Right? 1 option to choose from means 1 unique character to choose from, right? So the question that I'm asking is different. Here the question I was asking is which indexes are available, right? Here every time I was asking which indexes are available, which indexes are available. Here I'm asking which unique characters are available, which unique characters are available, right? So here let's see here. How many unique characters available here? Here, only one. Only one. So you have only one unique character available here. So again, the auxiliary array looks like BA, right? Only one option here. So this is the interesting thing, right? This, I hope you have not paid attention to here. I only had one unique character to choose from. That's why I choose A. Fine. What next? I guess it's done now. Here you only had one option, so now you have AAP, and similarly you have now ABA, and similarly here you have BAA. And these are the three possible permutations, right? These are the three possible permutations, right? And this actually turns out to be exactly what we discussed earlier, these three permutations, right? And if you observe it just a little bit, this strategy can be applied to like when all the characters unique as well. It's not limited to when you have duplicates. It's just like these are two approaches to solve the equation in same manner, and that's why I showed you. But this strategy also works. So at the bottommost level, again you have three permutations. Now as an example, what you can do is you can just dry run this on ABC, and it's gonna work the same way, guys. You will get all these 6 possible leaves which will have 6 permutations, right? The key idea was the question that I'm asking at each recursion step changes. Here I'm gonna ask what unique characters I have to choose from, what unique characters I have to choose from, what unique characters I have to choose from, right? So what is the pseudocode then? The pseudocode, let's write the pseudocode. So what is the pseudocode is, first we create the frequency map. We create the frequency map, right? So this you can create. Let's call it FM, or just call it FM, F, fine. And then what I'm gonna do is my recursive function is gonna be called solve. This time I'm not gonna pass string, I'm gonna pass the frequency map, auxiliary data structure, right? An auxiliary data structure, that's it, right? So in the recursion I only need two things this time. I only need two things, the frequency map and the auxiliary data structure. So that's what I'm gonna pass. Now let's see how this solve looks, right? Let's see how this solve looks, and then we can get a great idea about this. So solve, right? So how does this solve S and this auxiliary look? So what do you do here is you go for all the, let's say, character in F. Notice that this has to be sorted, F has to be sorted, otherwise you will not get the permutations in sorted order. So go through all the characters in F, then reduce the frequency, right? Go through all the unique characters in F, reduce the frequency, add it to aux dot push character, add it to the current permutation that you're considering, and then recurse, solve for S, solve for F, and new aux, right? And when you come back, that is when you have considered all the possible permutations starting with A, you have to clear the state. You have to add this one back, right? So when you are just coming back here and before starting with B, you have to add this, you have to convert this to 2 again, right? And make this empty again. So you have to do two things here. You will have to add f of ch plus plus, and then of course you'll have to do aux dot pop, right? So this you will have to do, and the base case is still same here. If length of aux has become n, you have got a permutation. So here instead of storing, you can just print it, right? And here you can just print aux, right? Here you can just print aux. So that's that. And how about the count? How are you going to get the count here, because you are not storing, right? So how are you going to get the count of all the permutation? That you can easily do. You can have the formula, right? N factorial about a factorial into b factorial. So this can be computed in order of n, right? In the brute force as well. So what is the time complexity here? So this is done, right? So this question is done. What is the time complexity? The time complexity here is simply n factorial for all the leaf nodes, because in the worst case, if the unique characters are there, there will be n factorial leaf nodes. N factorial into n. Why? Because you will have to print them, right? That's why n factorial into n. And space, we are not using any extra space, so it will be order of 1. But very important, there will be some space used by the recursion stack, right? So there will be some space used by the recursion stack. So I forgot to mention that you will call a function here, then you will call functions here, then you will call functions here, right? So your recursion stack grows. You'll start with n size, then you reach n minus 1, then n minus 2, so on and so forth. In the sense, this is, you can say, total elements to be considered, right? In the worst case, what can happen is all the characters can be unique. So at the first level, you have n characters to choose from. At the second level, you have n minus 1 to choose from. So the recursion stack will have some space. So that will be order of n, right? So that recursion stack space has to be order of n. On the same grounds, this guy, n factorial, also has order of n recursion stack space. It just it doesn't matter when you have n factorial very big. So this n was not counted, but here as well, right? In this case also, you will be consuming order of n recursion stack space. So this, I guess I forgot to mention. Sorry for that. So I'm mentioning right now. So in this case, we have reduced the space a lot. Now we have simply order of n space, and yeah, I mean, let's see the implementation. Now I hope you understood the approaches. If you have understood the approaches, like, please comment understood. I guess it was a pretty long video, but I enjoyed making it. Yeah, let's go to the coding part then. Alright, so finally it's time to look at the implementation. Let's first look at the implementation of the approach using frequency map. So of course I've taken the input here, and then in the frequency map approach, first we calculate the frequency map. The important thing is the keys have to be stored in sorted order. Otherwise you won't get the permutations in sorted manner. You will have to store them somewhere, and then, like, it defeats the purpose of saving space if you want to store the permutations again, right? So just create a map here. The time complexities won't change because it will just have maximum 26 letters. So we create a frequency map, right? And then we just output the number of unique permutations that we'll have. So I will just use the formula of permutation with repetition. And here, like, this fact function is simply order of n function. I just go from 1 to n and just calculate the permutation. So nothing fancy here. So till this part, everything is fine. Then the main function, the recursive function, it takes two things. First is the frequency map. Again is auxiliary storage. So I've defined it. And I'm also passing it n, the size of string, because I should know when to stop, right? And let's look at this print permutation function. Now, base case, simple. If we have considered all the characters, simply print it, not store it. So saving space there. Then I'm gonna consider all the possible 26 characters. Notice I'm not doing you can say I'm not iterating the map directly. Why? Because we have to modify the map. Now, while you are doing that iteration using for each loop and you modify the map, I think it messes up with the iterators or something like that. So please don't do that. It's not preferable, I guess. So that's why I've kept it simple. I've just gone through all the possible characters. If this character exists in the map, I'm gonna add it to my auxiliary array, reduce its frequency, and if it was the last occurrence of that character, I'm gonna erase it, right? If all the instances of this character is consumed, I'm gonna remove it, right? For example, if I have 2 A's and I've put all the 2 A's, then I have to remove it from the map, right? So that's what I'm doing, and then I'm gonna recur, right? The next step. And similarly, this is a backtracking step. We have to increase the frequency again. So once you've considered all these strings starting with, let's say, the first guy, when you are about to just start with the second unique character, you have to update your frequencies back. And this is, I also have to remove it from the temporary array, right? So that's what it is, the classical backtracking. So here, I guess sometimes beginners get confused most, but this you will get if you just draw the recursion tree yourself, okay? So yeah, I mean, that's the approach using flag array. The frequency map. Now let's see the approach using flag array. That would be interesting too, right? So only problem is it has a high space complexity and a logarithmic factor included in the total time, right? So flag array based approach, then let's see. So what it does is it again does the same thing. The recursive function takes string, flag array, and auxiliary permutation. Okay, so let's discuss the second approach, or you can say the bit less suboptimal approach in terms of time and space, which is using the flag array, right? So let's discuss that now. So in that approach, again same things happen, right? In the recursive function though, this time we are going to pass s, the flag array, initially marking that all the indexes are unused, and then we'll also need auxiliary storage where we'll store the current state of the permutation, and then we will need a set here. This time we are going to store elements in a set, right? The results, the permutations. Two reasons, right? Avoid repetitions and get them in sorted order. And once this function has done its magic, of course we are going to this function. We can just print the length of unique permutation, whatever this set has, right? What is the length of this set is. By the way, this length is not a standard C++ function. I've just defined as standard define if you are scratching your head above it. Fine. So that's one thing. And then I can just go through all the unique permutation and print it. Time complexity, I guess we already discussed. Let's go to this recursive function because that's the main thing which it is doing. Base condition is clear, right? If you have reached the end, if you have considered all the characters, then you can just insert it in the set of string, so that uniqueness maintained, sorted order maintained, you can just return it. Otherwise, try considering all the possible characters, right? But if a character is already in the, you can say already in the auxiliary array, don't continue it. Like, don't use it. Continue. Otherwise, add it to the augs, mark it used, recur, and then backtrack. Once you have considered all the characters starting with A, all the permutations starting with A, you have to, you can say, before you start considering all the permutations starting with the second guy, you have to reset the states. So that's what this is, right? So this is a classical backtracking step. And yeah, I mean, that's about the flag array based approach. There is one more approach, which is, you can say, using the next permutation STL function, which I can discuss, but I don't want to because that will be the most simplest solution for this question. Yet there's not much of a learning involved there. I guess the amount of learning that we have done till now in using that approach, it would have been, you can say, just instant, and this video would have been over in just 5 to 10 minutes. So what I want to do is, now I want to give you an exercise to Google that function, next permutation, or maybe I just link up, you can say, the documentation of the next permutation function. Read about it and tell me, like, in the comment section, how are you going to use that function to solve this question. I already gave you a hint, like it's going to solve this question in no time, like in a matter of minutes, since you already know a lot more than it is required now. So yeah, let's do that, right? And if you are stuck any which way, I have included how to do that. Okay, I just showed you, but the solution is there here, but I want you to try and paste it in the comment section. Fine. So I hope you got something out of this video. I'll see you in the next one.